Okay, folks, so since columns can be a little more burly than some of the other stuff we've done, I wanted to give you a little more video information introduction to columns to help you get started. So let's go ahead and dive in here. So on the left here we have a rebar cage, so vertical bars and then the ties which keep those in place. You can see a bend up here, so the column form is going to step to a smaller size. This is a finished floor or a couple finished columns with kind of a shallow beam type system. These types of beams are pretty inefficient, but sometimes the floor to floor height constraints drive beam sizes more than the beam efficiency. So the first thing we want to understand is columns are prone to buckling, where the column bows out long before it reaches its material strength. This is more true in timber and masonry, or rather steel columns. In concrete columns, if we keep our slenderness, so KL over R, so K being an effective length factor, L being the unbraced length, and R the radius of gyration. So R is the square root of moment of inertia over the area. We keep it under 22 for moment frames and under 28 for brace frames, then we can ignore slenderness. So we're going to live in this regime in this class. Now, if we had slender columns that were somewhat slender, we could use some ACI methods, or really slender, we would be using P-delta analysis. Okay, so this table just gives you some lengths of columns that you could ignore slenderness for a given column size. So this would be the least dimension of a rectangular column or of a square column. And again, it's all estimates here. So this is not like hardcore engineering. This is just get you started. Okay, effective length factors. We've seen this before. So a normal pin column, we'd have a K of 1. For a fixed, we'd have a K of 0.65. Okay, for more complicated building systems, which all of our columns will be in, we're actually going to use this nomograph, which relates the stiffness of the beams and columns at the top and bottom to get our K. So for a shear wall system that's non-sway, we'd have a K between 0.5 and 1. For moment frames, we're going to have a K between 1 and theoretically infinity, though something that flexible wouldn't stand up under its own load anyway. So this slide gives you kind of a determination. So G at A and G at B, you take the sum of the column stiffness over the lengths divided by the sum of the beam stiffness over their lengths, and you'll get a number. So you do that for the top and bottom joint. And then let's say we had 0.3 on one and 2 on another. You draw the line, and then you come to this K and you pick off the number. So it's 0.76 or so. Anyway, I'll let you dig into that more. Okay, so kind of the crux of columns are interaction diagrams. And this first dash curve is the nominal capacity curve. The second is the factored curve that has the phi factor applied to it. So you can see that the safety factor in this tension area and some of the bending, this is the tension control limit, the phi is 0.9, but then suddenly we go from a phi of 0.9 to a phi of 0.65 for the rest of the curve. And basically what this plots is flexural capacity versus axial capacity. And then what we'll do is from analysis, we'll find our load and moment, axial load and moment, and plot it in on the chart. And if it's inside of this curve, the column is safe. And if it's outside of that curve anywhere here, the column is unsafe. Okay, so we're going to look at some key strain conditions that will help us develop this interaction diagram. And yeah, it's tedious. So the first is pure compression, which is pretty straightforward, Phi 0.65. The second point is zero tension in the bar. The second is, or the third point is 50% yield in the bar. The third, or fourth point rather, is the bar yields when the concrete crushes. This point here is tension controlled, where we have 0.005 strain in the bar, which is about twice its yield strain. And then here is where we have no axial load, just pure bending. And then here we have pure tension. So you can see the phi factors are pretty much 0.65 all the way to point D, then they transition to 0.9 here. So this is that transition area we looked at in the fundamentals discussion. Okay, so let's just jump into strain distribution. So if we have a column and a bar layout, I like to start from the top and have the bottom layer my one layer, and the second my two, and the third my third layer. If we look at a strain distribution, we can say the strain in the steel in the bottom layer, or we maybe call this the outer layer, is linear to the crushing strain of the concrete of 0.003. This will always be 0.003. What we're going to do is change the strain in the outermost layer, and as that changes, we're going to get a line that kind of swings back and forth like this. And then using similar triangles, we can find the strain in each bar, just relating the crushing strain over C to the strain in the still layer, whatever ith layer, so I would be 1, 2, 3, or 4, divided by C minus the D dimension to that layer. So if I have the strain in still 3, I would use D of S3 right here. Okay, so there's some more relationships we can develop. So we can solve for C, we can solve for the strain in the ith bar. So these kind of take this previous equation and just make it something usable. Okay, so once we have the strain diagram, we want to convert the strain in the column to stress in the column. So to do that, we're going to say the stress, the compression diagram, or the compression is a block that's 0.5 times the F prime C, that's this dimension, and then A deep. And remember, A is going to be that beta 1 times C. So we have C times beta 1. That varies depending on the compressive strength of the concrete. For 4,000 psi mud, it's 0.85. Not to be confused with that 0.85. Okay, so the still stress, once we have strain, so we have strain at different locations, you can see that this strain here for 3 and 4 is compressive, and this strain here is tension strain. So we're going to have, if we multiply the strain times the modulus of elasticity, so 29 million psi times the strain we calculated, as long as that's less than the yield strength, then we'll use that. If it's more than the yield strength, we will say the strain is past the yield strain, and we'll use the actual yield strength. So this is kind of the fundamental equation to develop the stress diagram. So there'll be a stress in each bar. And then we want to develop the force diagram where we're taking the stress in each bar times its cross-sectional area. So here we have FS1, and maybe that's at yield, maybe it's not, but we'll multiply it times the area of the 4 bars right here. And then FS2 will multiply just by 2 bars, same with 3, but it's going to be in compression. And then FS4 is going to be multiplied by 4 bars. So we write this as FSI, so I being the numbers 1, 2, 3, 4 here, area being the area of these layers. This is the 1 layer, the 2 layer, the 3 and the 4 layer, times the stress that we calculated on the previous slide. Once we have that, we have a force distribution. We have a compressive force, which is just the A times 0.85 F prime C times the width this way of the beam. That gives us C, and that's what is reflected right here. All right, then we sum forces and moments. So we have our compressive force in the concrete plus the forces in the rebar. And then we do sum of moments to get the flexural capacity. So this gives us axial capacity, that gives us flexural capacity, and we just follow the nomenclature here. So basically we sum moments about this horizontal axis at the center line of the section. Okay, so with that said, let's look at the actual math or a little more in detail. Actually, let me start a new video just so this doesn't get too long. Okay, so moving on to various strain conditions along the interaction diagram. We'll start with pure compression. And what matters is the crushing strain in the concrete is 0.003. This corresponds to a stress in the concrete of 0.85 F prime C. And so to get the nominal axial strength, we'll have 0.85 F prime C times the gross area minus the still. So we're taking out the area of still when we multiply by the concrete strength. And then we add that yield strength of the still times its area back into the equation. And then if we get our nominal capacity, we have phi an extra 0.8, which, as far as I can tell, just accounts for kind of the reality of life and some buckling things. And then we have this equation repeated. So I would recommend using this equation straight up. Again, gross area of the concrete is the width times the height of the section, or B times H, etc. Okay, that one's pretty easy. Zero strain. Basically, at this bottom layer of rebar, we're going to say the strain is equal to 0 in the still. And then we have a direct linear relationship to the concrete crushing strain of 0.003. Okay, so using similar triangles, we can back out the strain in each bar. So I've repeated this equation from the previous slides. We can find the force in each bar, so ES times, capital ES times the strain. And I probably should add an I there. We want to make sure that's less than the yield strength. If it's more, then that's just not possible. And then we find the force in each bar by finding the area of the bar. So in layer 1, we would have 4 bars. In layer 2, we would only have 2 bars. Times the stress in the bar minus 0.85 F prime C. Okay, so once we have that, we can do a summation of forces. So we have the compression force in the concrete, and then we have 3 compression forces in the still. No tension in the still yet because there's 0 tension strain at the bar. So right here is the point of inflection, so to speak. This little part of concrete's in tension, but it doesn't really make much of a difference. Then we can also sum moments. So we have the compressive force times its distance to the center line. And then we have each still force times its distance to the center line. We run those numbers, we'll get Mn, we'll get Pn, and then phi is 0.65 in this case. Just a little reminder that A is equal to beta 1 times C. Okay, so that's that portion. And then we get to C here where retention is 50% of yield. So we'll say the strain, the key here is the strain in bar 1 in this layer, so it's not just one bar but multiple, is equal to 0.5 times the yield strain. And then we have a linear relationship to the concrete crushing strain. So similar to what we just did, we can come back to these equations and use them to get strain in the bar, stress in the bar, force in the bar, calculate the concrete compressive force, do a sum of forces. You can see this one now is in tension because it's going the opposite direction of those three things, and this one hardly counts because the strain is so small. Anyway, so we kind of just keep working this same method. So now if we go to a balance condition, that's where the strain in the concrete, or the concrete crushes when the rebar yields. So we'll say strain at bar layer 1 is at strain of yield, which would just be Fy over the modulus of elasticity. Just making a note to add that to the slide here. Okay, so in beams, we want to stay away from this point. So in beams, we're going to live kind of down in this regime, but in columns, we really don't have an option. So in this case, we now have our new strain distribution, and I go back a few slides. I'm going to use these same equations again. Don't need to derive anything new. I can just kind of reuse that same approach, sum of forces, sum of moments, and I can find what my capacity is, both axial and flexural capacity, and identify this point right here on my diagram. Okay, so moving on, we will look at the tension controlled. And so now we're going to say the strain in this bottom layer of steel is 0.005. So if you take 60 KSI bar divided by 29,000, which would be the elastic modulus, you get 0.0207. So this yield strain in the bar is double, or this strain in the bar is double the yield strain. Anyway, so again, we do the math. We can find C is equal to 0.375 D. It just turns out that's what it is. Again, we can use these equations. And we're going to do sum of forces, sum of moments, and get our capacities. Now, we're going to say we're 0.9 for our phi factor because we're tension controlled, which is defined by the fact that we used a strain in this bottom layer of bar of 0.005. Okay, then moving on, condition F is hard to find because you just have to kind of iterate on it to get there. So something that we can do is just draw a straight line between E and G, and it's pretty dang close. Another way to do this is to throw it in Excel or some kind of MathCAD, MATLAB, whatever program, and calc it. Another way is just to solve it by beam method like we did in chapter 4 or module 4 to find the flexural strength. So a couple options there. Basically, in this case, we have no axial capacity. It's all flexural capacity. So the sum of forces would equal 0 in this case. Sum of moments would not equal 0. Okay, and then the last slide, or the last calc, is we're going to find the tension capacity, this point here. And that's just ignoring the concrete strength, taking the yield strength, 60 KSI usually, times the area of all the steel, and then multiplying by 0.9. Once we do that, we get the nominal capacity curve, and we get the factored capacity curve. So then you say to yourself, well, that's cool. What do we do with it? So we're going to plot our axial and moment points based on analysis. So if I run 5 load combinations, or in this case 3, and I plot the moment demand and the axial demand as these little plus signs, These two are inside my curve. This one's outside. So this section actually isn't strong enough to carry the forces applied to it. Not by much, but enough that we don't want to have our points outside of this curve. So we would either change bar sizes, add bar, or go to a larger section. Okay, so that kind of wraps us up on the calculation part. I'll tell you now, it's not easy. It takes some time, so don't wait to start your homework till an hour before it's due, because that won't go so well. So just quickly to wrap up, there's a few more slides that talk about reinforcing limits. Generally, we want to be between 1% and 4% reinforcing to the area of the concrete. That tends to be pretty economical. Little bend detail, if you're going to bend the bars, have a 1 in 6 slope. Here's some reinforcing requirements for the transverse, so the ties. So some minimums on the spacing. We need to grab every other bar, so you can see this bar is grabbed by a tie, as is this one. This one doesn't count because it could move laterally. And then there's some spacing requirements. So this sketch is there to give you some more insight into those requirements. And then just a quick example. Here is an old column that has the ties about every foot, maybe even more apart, maybe 16 inches. You can see how poorly it performed in an earthquake, that the concrete crushed, fell out, and lost its vertical strength. Here you can see all of the concrete inside of the ties, because they're so tight. The concrete there is still there, even though the cover is mostly missing. This is what we want in an earthquake, is we want to have that core of concrete remaining in there with both the concrete and the vertical bars in place. Okay, so you guys can read that yourself. Hopefully this gives you a little bit of help getting started. And just for your enjoyment, there's an example that goes through the full blown calculation, starting with finding the column forces, which is this page, running load combinations, doing some initial sizing, and then walking through step by step this interaction diagram. So there's some strain distributions, hopefully super clear for you. It's in both metric and English, so if you don't want to do the metric, just ignore this stuff on the side. If you want to do metric, ignore the stuff on the left. Okay, so at the end of this example, let me just skip down there. There's an interaction diagram, which is for 8 number 11s and a 20-inch square 5,000 psi concrete. Here is the nominal capacity curve. This little dotted line is CRSI's manual, and then the factored curve is what I show here. And why CRSI is different, there's the reason right there. So anyway, let's call that good. I will see you in class, and we can get into all your questions on this, both examples and this PowerPoint slide on the interaction diagrams, which can be a little burdensome, but if you just take it one bite at a time, before you know it, you'll have eaten the elephant.